And then going to start. So today we will start with new topic. Okay. So it's regarding maybe then I need to change the color then in this case. I'll change it to this color to see. Oh yeah, it's pretty good. So what we are going, I'm going to admit. So today we are going to move to a new topic. We keep having students coming. So it's a new topic in our website, module 3. Okay, it's about algorithm complexity, so time complexity analysis, and we also call so complexity. So algorithm complexity, and a lot of time we also call time efficiency. Basically, there is a symbol called O something. You may see that a lot in computer science. Okay, so this is also classic computer science material. Okay, and algorithm analysis. And we have a class, CS300, and in that class, it's covered a lot more. Okay, it has a lot of math stuff also. Hold on, I need to admit the student. Okay, so and generally speaking, we have one more student coming. So over here, right now, we focus more. Keep having student coming. Focus more about time efficiency analysis. Okay, there is another, generally speaking, when you discuss algorithm, it's not just about time. A lot of time, you also consider about space efficiency. Okay, but nowadays we discuss more about time efficiency. Okay. So space is just analyze the memory, okay, efficiency. Okay, so it's so regarding any method, etc. So to do something, supposed to search, the very basic idea is about to search. Okay, you have sequence of items. Sequence of items you want to search, is it? So the brute force method is to do what? One by one comparison, is it? So one by one and following the sequence, is it? So that kind of search is what? Is a linear search. Linear search, is it? And for linear search, just think about you have all of the items, sequence of items, is it? And just think about the, so what we just said is the linear search is you need to do one by one comparison, is it? Until you find that specific item, is it? But if the item is at beginning, then that's the best scenario, is it? Because you do the comparison, you found it. So that's the best case. And if item is at back, at the very end, then you need to compare with everyone else, is it, in the sequence, and you find it. So that's the worst case. And generally any random item, so it's maybe somewhere in the middle in the sequence, is it? So average speaking, then it take like a half-ish, is it, a comparison? Okay, so if item located at the beginning part, it's very good. It doesn't take a lot of effort. If it's at the very, it's located towards the back end of the sequence, then it's take more as it than the average. Okay, so that search is brute force. You need to one by one, is it with all of the items, is a kind of, so it's a linear search. And so let's check with you all. Who still remembers beside linear search? What other search we learned? And we said that search is faster than linear search. Who still remember? How about this is the first quiz question? Who still remember?
Someone in the chat said binary search.
Oh, yes, very good. Is it? So it's binary search. Binary search, is it? And who still remember? I don't think we ever covered that. So for binary search, the idea is what? So this is a search item. This search item. So and all of the items so already arranged in some order, is it in ascending order? Assuming in ascending order, is it in ascending order? So binary search is what? Is you find the middle item, is it? And you compare with the item of the middle. If the item is less than the middle, you can throw away the right part, is it? Then you kind of shorten the search by half, is it? You can keep doing like this, is each time you shorten your search range by half, each time you shorten your search range by half, is it? And of course, compare with brute force, every single one, your search range is shortened more and more, is it? So that's why it's more efficient, is a binary search, we said. And later on we will see the math analysis, okay? So regarding algorithm, we said we want to classify algorithm by the time. We call time complexity, is it time efficiency? So generally, how do we figure that out? Is it? So we can use a big T and regarding some variable, is it this n represent the number of items in a sequence, in any kind of sequence, is it? So to clarify, then we want to find out the total number, the total time to execute this algorithm on an input of size n. Okay, so you want to find the time, okay? But find time is basically associated with each individual machine. The running time is going to be different, is it? So generally speaking, when we just have the code, how do we analyze? We are going to count the number of statements executed in the algorithm. We are going to, so the Tn is going to be used to represent the number of statements. It's not you count your program's length, no. It's count the number of times the statement totally going to be executed when your program is running. Okay, and we just use that as a measure for the time, to measure time. to measure time. Otherwise, you need to have timer set up. Is when your program starts to run, when it's end, how long it's going to take, etc. But generally, when you do just analyze the code, is that we can also kind of get the picture, how many times the statement going to be executed. Okay, so here is a key concept, it's the TN. Okay. Okay, then let's go to okay, the second slides. Maybe let me, okay. Okay, so we just discussed TN. This TN is measure time to execute an algorithm for n input data. Okay, but here, like I said, we measure number of statements being executed. Okay, but when you see algorithm analysis, we always see this. We call it BigOh. Is it? BigOh. So it's right like O. So for linear, like a linear search, when we write BigOh, we write O of n. Okay. And when we write like a binary search, when we write the BigOh, we write order of log 2n. Okay. So within the BigOh, we have some math expression. Is it math function? Is it math function? So how do you come up with this math function? Is it so? Basically, it's O. Within this O, we care about this Fn. So this Fn is some function. So it's some function on n. Some function on n. Okay, n is what? Is number of input data. Is it? And normally when you see the O, you will see n or n quadratic or log 2n or cube or 2n, something like that. Okay, not a specific comprehensive math function. It's just some single term math function. Okay. Okay, so then, so that's what we care about. So this is our goal. The goal is to find this Fn. Okay, and from our algorithm, we can calculate it. This can be calculated. Okay, and then from this Tn, then we are going to find this Fn. Okay, once from Tn we find that Fn, we say, okay, this algorithm's time efficiency, its complexity is order of Fn. Okay, so this is the BigOh notation. Okay, and you read it as order Fn. Okay, so order n squared, order log 2n, something like that. But just always kind of single term. Okay, single term. Then what does this mean? Is it, so what this can tell us? This generally can tell us is as n increases, okay, how the time execution is also going to be increased with some rate. That's what you care. Okay, the rate as Fn. Okay, so the idea basically is going to be like this kind of trend, linear or log or quadratic or power, is it? So this will tell you this kind of, this rate increase. Okay, so this is the number of inputs. This is the time to finish your program, is it to finish your algorithm. Then just think about, so if I draw a vertical line, is it suppose this is a million items, is it this represent a million items, then which one do you think is the most efficient? Suppose this is log 2n, this is n linear, this is n quadratic, this is 2 to the n. Then based on this diagram, how about this going to be the second quiz question? So based on your math, so among these four, which one takes longest? Which one takes the longest? And which one takes the shortest? Based on this diagram. So this is a pure math question, is it? So who can tell me which one takes the longest and which one takes the shortest? Which one is going to be the fastest? Which one is going to be the slowest?
2 to n is longest.
Yeah.
Log n is faster.
Yeah. So this takes the longest. This is the fastest. It's purely based on math. Is it? And this also tells us another kind of idea. Is it when n increase? Is it certain numbers? Is it which takes more time each time when n increases, like by 1, by 2, or by 3? Which one grows faster? Of course, 2 to n also grows faster, is it? Then regarding algorithm, which one you like, you prefer? When you design an algorithm, suppose company A sells log 2n, company B sells n, company C sells n squared, company D sells 2 to n. Regarding tackle the same task, you have 4 companies to bid, then which one you are going to choose? Definitely A. Is it because it runs the fastest? Is it? You always want your algorithm to run fastest. Is it? Yeah. So that's what. Hold on, we have one student coming. So this is regarding algorithm. That's Fn. Okay, Fn just tells us when n increase, is it? When n increase, the rate, okay, the rate of your algorithm increases as that Fn, okay, as Fn. And then how do we find out from Tn to Fn? As it later on we will see. So generally speaking, we said Tn is order Fn if you can find some constant. If you can find, okay, just exist one is enough, so that you can have this expression hold true. The Tn, that's the real number of the execution times of the statement, less than the constant times that Fn. If you can guarantee this expression, then we can say, okay, Tn is order of Fn. Okay, then you see that Fn is the big O notation, is it? Okay, so that's regarding Tn and Fn's relation. Okay, then next let's take a look at examples, okay? So sometimes for some algorithm, no matter how many millions or billions of input data, you run that algorithm always the same amount of time. We call that a constant time. To represent constant time, we always represent order of 1. Okay, order of 1. So this represents constant time. Okay, constant time, no matter how large n is. Okay, so it's independent of the input size. Is it? One example is, if you recall, for stack, we have that pushback operation. Is it? You add that back. Is it? That's constant. It doesn't matter how large your data is, always added back. Is it? Yeah, so then that operation is constant time. Okay, then next, let's see this example. Maybe this looks better. Okay. So let's see, how do we find the big O? Okay, so here we have some algorithm. So in this example, suppose this is what the algorithm looks like. Okay, we don't care what it is. Okay, it's just some algorithm. So how do we analyze its time efficiency? Is it the complexity? Is we count the number of times it's going to be executed, the total number of times of statement. Okay, for this first statement, of course, it only executed once. Is it? And then for this while loop statement itself, how many times? When I start at 0 all the way to n, it's going to be what? N plus 1 times. Is it n plus 1 time? And then this assignment statement, how many times it's going to be executed? N times. Is it? Because when I is n, it's not going to go inside the loop. Is it? So that's 1 less than the loop statement itself. Is it? And how many times this is going to be executed? Also n times. Is it n time? And then we can add all of them together. Is it? So sigma is what? 1 plus n plus 1 plus n plus n. Is it? It's a summation. Is it? So what the value is? It's going to be 3n plus 2. Is it? Okay, so this is our Tn. Tn is 3n plus 2. Is it? And we wanted to find that Fn. Is it Fn? Fn, how do we find? We said, okay, if Tn less or equal than some constant times Fn. Is it times Fn? Okay, so this is a polynomial. Is it? And generally speaking, when you have a polynomial, you pick the highest order term. So we pick this n. Is it that linear? As our Fn, so we pick the highest order term n as our Fn. And then our question is what the C is going to be. As you can find, say here we said, how about we pick 6? Is it? Okay, if I do 6, C as 6, then you can always guarantee this comparison is true. Is it? You can always make sure this is true. And if this is true, that means what? Fn is n. And that is n. So we just say, okay, Tn is order n. Okay, it's order n. So what does this mean? Okay, that means if n doubles, Tn also doubles. It's a linear relationship, is it? So it's a linear relationship. Okay, so that's how we come up with, okay, so that's how we come up with that Fn. Okay, so this is the simplest case. And then next, let's take a look at the next example. the second one. Okay, let's take a look at this case. This time we have two loops. Is it outer loop and inner loop? How many times the outer loop, this loop is going to be executed? N plus 1. Is it N plus 1? Okay. Then how about inner loop? Here you need to be careful. Is it here you need to be careful? The loop statement itself. So this one, J will loop from 0 to N. Is it totally how many times this statement will be executed? Okay, when I is 0, J will loop from 0 to N. When I is 1, J will still be loop from 0 to N. Is it? And till I is what? N minus 1. J will loop between 0 to N. Is it? So anyway, each time the outer loop, so for each iteration on outer loop, how many times this inner loop are going to be executed? N plus 1. Is it? Then totally how many times the inner loop itself is going to be executed? Is going to be repeated how many times? N times. Is it? That's how we come up with N times N plus 1 for this loop, inner loop statement itself. Is it? And then anyway, internal, we are going to do something. And this internal do something, it's similar. As it do something, it's a loop N times the inner loop. Is it? And the outer loop, it's N. So it's N times N. Is it? And what is that Tn? And Tn, then you're going to add all three together. Is it? So N plus 1, N times N plus 1, and N squared. Is it? What is it? It's, we can find, it's 2n squared, 2n plus 1. Is it? And we said we always just care the highest order term. Is it? So we are going to pick Fn as n squared. And we also don't worry about whatever the coefficient it is. Okay, we just care about the term itself, because basically what the BigOh care about is the trend, is a trend. So we just pick the highest order term is n squared. Then the question, we want to find that C times Fn, that constant. Suppose here we pick 6. Is it? We can always guarantee this is true. Is it? This is true. So that's why we say, okay, Tn this time it's also order of n quadratic, is it n squared. So what this tells us, this just tells us when n doubles, Tn, it will take 4 times as big. Is it? When it triple, it will take 9 times. Then think about compare with linear. Of course, this takes longer. Is it? This takes longer. Okay, so that's the second example. And then next, let's take a look at the next example. Oh, so here we just gave some general examples. Okay, so polynomial, is it? So anyway, no matter what the polynomial quadratic, is it? No matter what the coefficient is, it's all considered the same order. Okay, consider, because what here we care about is more about the trend, it's not the exact time. Okay, we care about the level. Is it a linear level or log level or quadratic level? Is it? That's why we just pick the highest order term. So then in this regarding n squared versus 5, n squared versus 10, n squared, it doesn't matter. It's all just n squared. Okay, n squared. Okay, so then in this case, it's n squared. And this for 1 plus 2 plus, so this is called Gauss number or something, is it? Yeah, it's there is some stories that the mathematician Gauss, when he was a very, very little child, maybe 5 or some years old, he knows how to quickly. He wants to do the brute force one by one. That he will add the first and the last, and the second last. You do the pair because it's all the same. That it's all n. Then you just count how many pair. That and the pairs. That so pairs is n minus 2. So that's how you come up with this faster, okay, the calculation. So anyway, it's also what? The n quadratic, this kind. And the general, so like over here to list, common values for big O is what? Linear, quadratic, log 2, n log 2, 2 to n. Okay, something like this. So here give us more generalization. Okay, and regarding the comparison, okay, comparison. And we can see if you draw the curve, you will find log 2 is faster than linear. Linear definitely is faster than n times log. Is it? N is faster than n squared faster than n cubed. This is very slow, okay? 2 to n is very slow. And we can see it quite clear. If your input data is 64, is it? If log 2 is just 6 and 64, and give us, is it? If you go to 2 to 64, it's already go to this huge number. Is it this huge number? Think about it, even it's just a second, is it? And I don't know, is it go to year or just go to months? Then just think about if one algorithm company, one algorithm takes 6 seconds, and a company like F's algorithm takes this longer. Of course, you want to buy the algorithm that's just take 6 seconds, is it? So here it tells us the scale, okay. Okay, and here we have kind of clear the curve for the comparison, is it? So log, linear, 2 to n squared, quadratic, and 2 to n, is it? You can see the difference, is it? Clearly. And let's see. So here's and this is very old data, okay, very old data. And if you run the with the current days computer, the data will not be like this, okay. But anyway, this is just give us a comparison about n and their order, is it? When n is 10 to 1,000, is it? And if you take a look, go to log n, it takes from this second to 1,000th second, is it? But for 2 to n, you can see the huge difference. It's from 0.1 second can go to what? Go to, it says, go to too big to compute. And if it's n is 100, said already go to centuries. When n changes from 10 to 50, this already changed from 0.1 second to some 1,000 years. Is it? And if you take a look like linear, is it? It's not that large. Is it? N squared, it's still tolerable. But 2 to n, you can see it's intolerable. Is it? So that's why we say it's, so the big O, is it big O? It cares about the algorithms increasing rate, is it? With the increase. increase of n. Is it? It's a rate we can see. This 2 to n is really still quadratic. It's also not a very good way, is it? Okay, so here just gave us the reason why we need to analyze algorithm efficiency. Okay. And let's take a look more example. Is it? Yeah, so first is about the sequential search, linear search. Is it? Suppose we want to do linear search for an array. Is it? Okay, you have the loop. Okay, so this will take n plus 1 time. And how many times? Comparison n times. Is it? And you either go here or you go here. So that's why we just count here as 1 time. And then you add them up. So Tn, and then you add all of them up, it's 2n plus n. And we already know with polynomial, it's order of n, is it? Yeah, so that's sequential search. And then let's take a look, binary search. As a binary search, we kind of already know the idea, okay? So here's some algorithm to binary search, okay. First, we have the code, okay, 1 time. Okay, this statement going to be execute 1 time. And then it's a loop, is it? And keep dividing by 2. So you originally have this big. And then you go to, so cut by half. Then maybe you go here. Then you cut another half, maybe here. Then you cut another half, maybe here, is it? So you keep cut by half, is it? So the question is how many times you need to cut by half? We don't know, is it? So you can assume it's k times. Okay, later on we will see how do we figure out this k times, is it? Okay, the k time, and then internally of this won't go beyond k times. Is it? Because anyway, it's within the loop, is it? And we know it cannot go beyond k times, is it? Okay, so the question, how many k times? It's how many times it's going to be divided? Is it divided? Then you can just think about some number. If you have 16 number divided by 2, then it's 8. 8 divided by 4, 4 divided by it's 2, 2 divided by another 2, it's 1, is it? And when you have 1, then we can stop, is it? How many times? 1, 1, then 2, then 3, then 4, is it? It's 4 times. Basically 16 is what? It's 2 to 4, is it? So 2 to 4, and then you divide by, so k in this case is 4, is it? And if you have 32 is what? It's k is 5, is it? If you have 64, k is what? Is 6. If you have 128, then k is 7. Is it? 256 is 8. K is 8, something like this. 5, 12, k is 9, is it? 10, 24, k is 10, is it? And we're quite familiar with those 2 to k numbers, is it? And for other number like it's 10, 25, then we know it's almost 10 times if you want to divide by 2, is it? But how do we figure out, is it? So then assuming you have n, so the input size is n, is it? And it's going to be divided by 2 k times, is it? And for binary search, and then the final set size is 1. Then you stop, is it? So let's see, okay, and you need to divide by 2, is it? Okay, and then divide by 2. First divide by 2, and then second divide by 2, is it? Then third divide by 2, Okay, and you're going to do k divided by 2. Is it? After that, what your size is? Your size should less than 2. Is it? Because it's 1. Is it? It's 1. Okay, so we have this expression. N divided by 2 to k. Is it? This is going to determine the final step size. And we stop. So it's less than 2. Is it? And we can times 2 to k on both sides. So you can have n less than 2 times 2 to k. Is it? You times 2 to k. You times 2 to k. Is it? And you cross out this 2. That's how we come up with this expression. So this is our math expression. Is it? You know that. And what is this? This is 2 to k plus 1. Is it? And we have this, we can take a log 2. Is it? On both sides at the same time. Is it? What is this? Log 2 to k. Is it? That is what? This is k plus 1. Is it? Okay. And then based on this, basically the k is what? We just take the integer part, is it? So basically it's integer part of this log 2n is our k. Is it? It's our k. And if you take a look at those numbers, 2 to 10, 2 to, it's exactly the same. Is it? It's that same. Okay, so that's why for binary search, if input data size is n, okay, and I ask you how many times. So how many times going to be the divide by 2, is it? Divided by 2 is what? Is the log 2n. Okay, that's how we come up with this number, log 2n. Okay, and all of this cannot go beyond, is it? Cannot go beyond log 2n, is it? And if you analyze this whole algorithm, this is constant. This is log 2, cannot go beyond. So for the final Tn, the highest order term of the polynomial is what? It's going to be log 2n. Is it? It's going to be log 2n. So that's why we said the big O is just order log 2n. Okay, that's how we come up with binary search, is order of log 2n. Okay, and the linear is what? Linear search is order of n. So which one is faster? Is binary. But of course, for binary, it has the you need to also do sorting. Is it sort in ascending order? Is it? But if all of the item already sorted, then this is going to be faster. Okay. Okay, so that's regarding binary search. We kind of understand the idea. And next, let's take a look. We already learned the sorting algorithm. So let's take a look. First is a selection sort. Is it? Selection sort is what? Is what? Each round, you need to find the smallest item in that sublist. Then you swap. That's a selection sort. Okay. So anyway, here is a general algorithm for selection sort. Let's take a look. So over here, we loop from 0 all the way to n minus 1. Totally how many times? N times. Okay, including I equals n minus 1. Okay. And this I, how many times this is going to be executed? This is going to be n minus 1 time. Is it n minus 1 time? And then for the inner loop. But here we need to be careful for the inner loop j. J depends on I. As it j depends on I. So let's take a look here. When I is 0, j will loop from what? J will loop from 1 to n. Is it 1 to n? So totally how many times? 1 to n. It's what? It's until n plus 1. Is it? So that's how we come up with this number. Is it? And when I is 1, j from what? From 2 to n. Is it? How many times? N. Is it? And when I is 2, then j starts with what? From 3 to n. Is it? That's how you come with n minus 1. Is it? And you keep doing like this. Is it? Until j is what? J is n minus 2. Is it? And plus 1. Is it? How many times? That's going to be executed. Is it? So anyway, it's kind of the sequence number added together from 2 to n plus 1. Is it? You're going to add all of them together. And the inner loop, is it? The comparison statement, how many times it's going to be executed, it cannot go beyond this number. Is it? And from previous discussion, you remember we said 1 plus 2 plus 3 all the way to n. Is it? This kind of sequence number, if you add them together, it's going to be what? The highest order term is what? It's n squared. Is that we know that. So anyway, so all of this will not go beyond n squared. Is the highest order term. Is it? Okay, so then we know this is just linear. Is it? This is also linear. And here we have quadratic. So highest order term is quadratic. So the final total, the Tn, highest term, order term. Anyway, it's a polynomial. Is it? It's going to be n quadratic. Is it n quadratic? So that's why we see selection sort is order n squared. Okay, n squared. That's how we come up with this answer. Okay, and then next, let's see. That's a selection. Next, let's take a look. A quick sort. Okay. Sorting algorithm we already discussed, is it? And the quick sort we discuss is what? It's recursively executed, is it? And we say, okay, if the first, so index not go beyond last index, then you do split, then you quick sort yourself, is it? And there's no loop here, it's recursively call, is it? But the time, but the question is, how do you know how many times it's going to be recursively executed? So it's based on that split, how many times you need to split. But from binary search analysis, we know split by half, generally speaking is what? Is log 2n. That's just general, okay? Be very careful here. Generally speaking, is it? Generally speaking is log 2n. Is it? Log 2n. And for the split operation itself, the split, you remember it's a scan from right and scan from left. Is it? When you do scan at most is n, because the length of your array is n. Is at most is n. Is it? It's n. Okay, and then you recursively call. Is it? So this kind of like outer loop is log 2n, and the inner loop split itself is n, but it's also based on the recursive, the outer loop log 2n. Is it? So that's going to be n log 2n. That's how we come up with quick sort is n log 2n. Is it? N log 2n is less than n quadratic. Is it? This is selection sort. Selection sort. Okay, this is quick sort, but this is just generally speaking. Okay, generally speaking. And generally speaking, a split is log 2n. So can anyone figure out in which scenario? So in which case? In which case it's not a split, is not log 2n. Is not log 2n. Just think about if you have 1, 2, 3, 4, 5, 6. Suppose it's already in ascending order, and if this is a pivot, where you have divide by 2, no. That's because each time this, it's just your sublist. Is it? So this won't go with the log 2. Is it? Or the reverse order. Is it? So then in that case, quick sort is not going to have log 2n. So n log 2n is just an average case. Average case. Okay, average case. So that's we need to be careful. Okay. Okay, so that's regarding quick sort. Okay, it's how we analyze. So here the concept regarding quick sort and binary search, you can kind of, it's split by 2, is it? But for binary search, it's always divide by 2, is it? But for quick sort, it's not always, is it? It depends on the number, how it is arranged, is it? Because it's reverse order. Reverse order, is it? Reverse order. There it's also different story, is it? When you do divide by when you do that divide by 2, is it? So it cannot, because it's just it's tilted to one side. Okay, tilted to one side. Okay, so that's regarding quick sort. Okay, quick sort, so n log 2 is just an average case. Okay. And then next, let's see. Okay, so here we have another concept, because regarding quick sort, it's recursive, is it? So how do we do the time complexity? So sometimes we also time efficiency. Okay, so anyway, this BigOh, okay, it's also called time complexity analysis. Okay, so here the idea is for recursive, we call it recurrences relation analysis. Okay, so for this kind, how do we find out? So there is a way to do it. Okay, in math, you may also learn this kind of analysis called recurrency analysis. Okay, so let's take a look. The power, mass power is x 2 to the n calculation, is it? And of course, you can write with iterative way, is it? And for iterative, who can guess what's its order? iterative implementation. Who can guess what's the order for the power calculation using iterative way? What's going to be the order? Who can guess? Let's see. Yeah, someone said it's linear. Is it? Yeah, that is right. So it's linear. Is it linear? Let's take a look for this recursive case. Okay, recursive case. Okay, this is a stopping case. Execute one time, and you execute one time. Is it? But here you recursively call. Is it? You recursive call to what? X2 to n minus 1. Is it n minus 1? N minus 1. So assuming this Tn. Tn is for the power for this method. Is it? And when you call power of n minus 1, then what is T? It's Tn minus 1. Is it? That's understandable. Is it? Then it's going to be Tn minus 1. And then if you keep calling, is it? Then it's going to call what? It's going to call x times power of x n minus 2. Is it? And what is the time complexity? Then it's going to be Tn minus 2. Is it? And this can be decomposed to x times power of x n minus 3. And what is this? This is going to be time t of n minus 3. Is it? You're going to keep having this kind of relation. Is it? Until like t is 1. Is it? The size has 1. So, okay. So what's going to be? So Tn is going to be what? 1 time plus Tn minus 1 time. Is it? So this is true. This hold true. Is it? So we share. Okay, then Tn minus 1, if we rewrite as T minus 2, it's going to be 2 plus Tn minus 2. Is it? This part. Is it? So this, and then we can decompose this as what? As 2 plus Tn minus 3. Is it? And then you can keep doing. Is it? Until you have 2 plus T1. Is it? T plus T1. That's the last decomposing. But you keep having a lot of 2. Is it a lot of 2? Is it a lot of 2? And the T1 is what? T1 is 2. Is it? It is 2. Is it? So totally how many times previously you do n minus 1? Decomposing. Is it? So that's why, that's how, totally how many 2 we have? We have n. Is it? That's how you come up with its Tn is 2n. Is it 2n? So what is order in the recurrency relation? It's order of n. Okay, that's how we, so even with the recursive version of the power, it's also order of n. Okay, order of n. Okay, so that's regarding this part of analysis. Let's take a look at our textbook, what our textbook gave us. Okay, I'm going to, and this is in chapter 22, okay. Developer, let's see, quickly go over. Grocery, basically we already cover best case, average case, and the worst case, is it? And so when we analyze the algorithm, is it, if you recall, do you recall like the bubble sort? Exchange sort, is it? And at that time, I remember I mentioned, is it what's the best case and what's the worst case? Is it worst case and the average case? And who still remember what's the best case?
ON.
No, I don't mean order of what. I don't mean that. What I mean, when the best case is for bubble sort.
When it is sorted.
Yeah, when it is already sorted. Is it? Then that's the best case. Is it? That's the best case. So like some of you just mentioned, it's what? It's linear. Is it? Because you just do the comparison. Is it? When it will be the worst case? The worst case, when?
When it is in descending order.
Yeah, so it's a reverse order. Reverse order. Is it? And as to the order, we haven't analyzed. Okay, but we can analyze. Is it? The average case, just some sorted, some not sorted. Is it? Okay, so then just think about it. Okay, so generally speaking, best case, when you design an algorithm, it's not always happen. Is that if you use that to represent this order, that's not a good design. Okay, so we don't use best case to represent. Okay, average case, it's also hard to analyze. Is it? It's hard. Okay, it's not ideal. Is it? But for the worst case, okay, when you see the code, is it? And in the worst scenario, is it? And this a lot of time it's still analyzable. It's easy to analyzable, is it? So a lot of time when we discuss the order, we use the worst case. Okay, we use the worst case. A lot of time when you see that order, it may represent the worst case. So, but that's not true for quicksort. Quicksort is not that case, okay? Quicksort average case is n log 2n. The worst case is n quadratic. Okay, it's n trial. And then in that case, generally we said quicksort is faster. Is that when we said the libraries algorithm, they implemented using quicksort. Why? Because it's average case, it's improved. Is it not? And of course, the worst case, because you cannot split by 2, is that it's tilted in one way, is it? That's why then in that case, it's not the best representable, is it? Okay, but like I just said, a lot of time when we discuss algorithm, we will also see a lot of time average and the worst are the same, is it? And then we said worst case can be used to represent that big O, okay? So this is regarding best case, worst case, and average case, okay? And we already explained the multiplicative constant doesn't matter. We just care the highest order term, is it? Okay, so here I also gave some useful math summations. Is it like this is the Gauss number? Is it? Shouldn't call Gauss number. It's he finds the best way to calculate it. Okay, so this is n times n plus 1 divided by 2. Anyway, it's n squared. That's what we care, is it? And we also have this kind of sequence, is it? So it's always multiplicative, is it? And then in this case, it's the math. In math, you learn that it's a2 to the n plus 1 minus 1 divided by a minus 1, is it? And we use this a lot, is it? It's 2 to the n it's 2 to 0 plus 2 to 1 plus all the way to 2 to n, is it? And basically this is what, 2 to n plus 1 minus 1, is it? And generally we also say it's 2 to n, is it? 2 to n, okay. So that's just some use for summations, okay. And the repetition we kind of already went over, is it, in the detailed example, how to analyze, okay. Constant time we already discussed, linear binary search we already discussed, and binary search analyzing how do we come up with log 2, is it, we also discussed, okay. And selection sort we also discussed, quadratic, okay. And here we can also take a look at this one, okay. Tower of Hanoi, if you recall, and I remember in CS2 we discussed the recursive approach to achieve that Tower of Hanoi game, is it? And generally speaking, how it works is you move the first n plus 1 plates, is it, from source to destination with the help of the spare. That's how it works. And then you, because assuming it's already moved, it's already, then you move what? The largest, is it? So this is the largest, is it? From a, oh, I'm sorry. So this is the spare one. Okay, because this is the source. Source, this is destination, B is destination, okay. So we use the spare one, is it? You assuming the spare one going to hold the top n minus 1, is it? And then you have the largest one, is it? So it's just one step. You move it from source to destination, to destination. And then you're going to apply the same strategy to get this top n minus 1 to the destination. Is it to the destination with the assist of the source? Is it? So that's how that algorithm works, is it? And regarding the TN analysis, is it? This also follows that recurrence relationship, is it? Analysis. In math, is that you learn that recurrence, how to do that. So this equals Tn minus 1 Tn. So that's represent the first step, and this recursive step, is it, those two recursive, it's n minus 1, is it? And anyway, so that's one time, so adding some constant c, is it? And this is going to be expressed like this. And we can further decompose Tn minus 1 as T minus 2's case, is it? So it's going to be 2 times T n minus 2 plus some constant, is it? And you can keep doing like this, is it? Until you only have one disk, is it? And it's going to be 2 to n minus 1, is it? 2 to n minus 1. And finally, is it? And we can, so finally we can come up with this as what? C times 2 to the n minus 1, then c times 2 to n. So you have all the common constant c, is it? So you can get move off this out, is it? That's why you have this 2 to the n minus 1 plus 2 to n minus 2 all the way to 1, is it? And then we know this sequence, is it? So it's going to be 2 to n minus 1, is it? So that's how you come up. If Tower of Hanoi and the BigOh analysis, you can find its order of 2 to the n. Okay, order of 2 to the n. Okay, so this is another example about that recurrence analysis. Okay, let's see what more we have. Okay, here it gave us more. It says common recurrence relations. Okay, common relation. So this is kind of, you see, divide by 2. Is it like a binary search? Is it binary search? Then in this case, it's log 2n. Is it log 2n? Okay, and we also see that power, is it power is decomposed to what? N minus 1, is it? And regarding linear search, you can also do something like this. Each time you shorten your search list by 1, is it, if you apply the recursive way, is it? So it can also be decomposed to what? To N minus 1 plus something, is it? This can further be decomposed to N minus 2, is it? Plus some constant, is it? You can keep doing like this, is it? So if it is this kind of recurrence, then the order is going to be linear, is it linear? Okay, and similar for this, nothing, not a lot of change, is it? And what is this kind of case? Okay, this kind of case is like, if you recall, we just said the quick sort, merge sort, is it all same? It's half, is it? You decompose by half and plus some linear thing, is it? So then in this case, it's n log 2n. Okay, n log 2n. And this is another kind of recurrence. And then you can come up with n log 2n. Okay. And we also have, if decomposed to n minus 1, but you have linear, is it? So like a selection sort or insertion sort, is it? Then in this case, it's n quadratic. Okay. And Tower of Hanoi, it's 2 times Tn, is it? You're going to decompose at 2 of this. Then in this case, it's 2 to the n. Okay, 2 to the n. And the Fibonacci algorithm, if you implement, generally speaking, Fibonacci, we don't need to do recursive. It can be completed with iterative way, is it? But you can also do recursive, is it? Recursive is the previous two's result, is it? That's how you come up with Tn minus 1, Tn minus 2, is it? Then in this case, it's going to be what? 2 to the n. Okay, Fibonacci, if you use the iterative way, and who can guess for iterative way? Iterative implementation of Fibonacci. Who can guess what's going to be the big O?
Would it be O to the n?
Yeah, it's just n. It's linear, is it? Because it's just the for loop, you can achieve that, is it? So, am I right? The iterative way. Yeah, I think I'm right. Yeah, so it's linear. So with recursive, then clearly from the big O, we can see this is not efficient. Is it not efficient? So clearly, even just with this big O analysis, okay. And I think today we just stop here. So then Thursday we can continue our discussion.